So today we cover the principle of net net force. Okay, so net force. So the only time that you really need to pay super attention to a net force is whenever there's what there is more than one force acting on an object. Yes, yes. Okay. Uh, okay. Why don't you need to why don't you need to understand? Not to understand. Why don't you need to deal with net force when you only have one force? Because if you have one force, that would be your what? Your net force. Okay. But if you have multiple ones, they might what? They might actually what? Deal differently with each other. Okay. So a not so new quantity must be defined. That new quantity is called net force. Okay. By the way, can you give me another word for the word net, like a synonym for the word net? Overall, yes. Or, for example, what? Yeah, net. Okay, so when you calculate your net income, really, what happens? Let's say, for example, that you're taking Miss Farawi's, business accounting class, and she asks you to, what? Let's say that she makes a situation like you graduated, and let's say, for example, you're an engineer, and you're just making an Excel sheet for your own income. How do you calculate your net income? You have a bunch of what? Money is either what coming in or So that means what? Every entry in your Excel sheet is either gonna be what positive or, and that's the key. That's why, which is, by the way, positive and negative with forces. What does that also mean with forces or kinematics? Did we use positive and negatives? Sorry, say again. Okay, accelerating. When did we really need to? When did we actually deal with positives and negatives in kinematics? When we also dealt with what? What did we use to deal with? And then we were like, I don't need to deal with these. I can just call them positives and negatives. Directions, vectors, exactly. So that's why net force also has the idea of what forces could add up or add up or cancel out. Yeah, so they could increase their effect or what? Decrease their effect. Okay, perfect. So the net force in simplest term, as Ali said, is the overall force that basically combines the effect of all the other forces acting on the object. Okay, everyone, this is important. From the outside, we never ever care about what? About the object acting on the about the forces acting on the object from the inside. So, for example, if you're analyzing the motion of a car, you could not care less what is affecting the car on the inside. You are only caring about what affects the car from the outside. Like what? Like gravity, like normal, like friction, like, for example, the thrust or the engine power. But you really don't care, for example, about, oh, what force is the person inside of the car exerting or applying on the seat? That doesn't affect the motion of the car in any way. That does affect the what? The situation of the driver, but not the car itself. So always know that you can never look at an object what internally. You only look at what externally. Thank you. You always care about things from the outside. Okay. If you're looking on the inside, that means that inside becomes the what? Becomes the new environment, and you have to look at the outside of that inside as well. Okay. Since forces are what I just alluded when I discussed it with Baha right now, are vectors by nature, they must be combined. I don't like the word added. I like the word what? Combined, because the word combined could cover what? Adding or subtraction. Yes. Although technically, when you subtract, you also could think of it as what? Adding, but you're adding what kind of values? Negative. Thank you. The subtraction is technically a what? A special case of what? Of addition, but we just have negatives associated with it. Okay? So since forces are vectors by nature, they must be combined with their directions in mind, not just their magnitude. For example, everyone, Hamid, okay, hold on this pen. Okay, everyone, is the pen moving? Okay, what does that tell you about my force and his force? They have to be what? They have to be identical and equal. So imagine if so technically, if it's not moving, what's the net force on the pen? If you just said, oh, I'm not going to care about direction, I'm just going to care about magnitude. Let's say he pulls with 10 newtons, and I also have to pull with what? What's 10 plus 10? But that doesn't make sense because the force has to be what? 0. So what was my mistake? I dealt with them as vectors or just scalars? I just dealt with them as scalars. I should have dealt with them as what? Vectors. 10 east plus 10 west is equal to what? 0 newton. There you go. So please always remember that forces need to have the directions in mind whenever you add them up. Okay? All right. Next slide. Okay. Everyone, Why are those two statements not equivalent? Don't look at the slide. Just look at the statements and just tell me, why do you think they do not mean the same thing, even though they're, I can't say identical, they're very similar. The first one is saying the net force on the object is zero. And the other one, the forces on the object are zero. How come they do not mean the same thing? To someone who didn't do physics, they're like, that's not like the same thing. It's not. Why? Say it in your own words. I know I cannot provide some explanation there, but try to think of it in your own words. I don't give you a lot of communication questions, but maybe once in a while. Uday. So, okay, give me examples where those two statements, actual examples where those two statements are not the same. I'll give you a hint. Me and Muhammad just did one of them. The pen thing. The pen thing that we did applies with which statement? The first or the second? Hmm. What we did. Hold again. This is which one? Is this the first statement or the second statement? So how many people say second? How many people say first? Okay. Okay. Yes, first. All right. Mariam, why is it the first? Okay. Was the pen moving? So was the pen moving? But did you see us exert forces on it? Which means there were forces there, but they were doing what to each other? Canceling each other. Again, remember, cancel. That's why I don't like to say what, for example, this right here. Is it moving? There has to be a force, not canceling gravity. I don't like the word cancel. I like the word what I said yesterday. Starts with B. Balancing. Because when you cancel gravity, legit, what happens? There is no gravity on the object. Is there still gravity on it? But something else is what? Yeah, well, no. Gravity pushing it up. Gravity is not being canceled. It's being what? Balanced. Remember, canceling, you can say cancel the effect, right? Not canceling the force itself. Can someone tell me where then would this statement be true? When are the forces on object all zero? Okay, huh? Space. Right now, you could say what? Are the forces on this one zero? No way, because it's affected by what? When do you really have no forces on an object? When you are what? In theoretical what? Deep space. Because then you don't have what? You don't have gravity. Or what? Gravitation. Or what? Friction. Or normal. Or applied. Or tension. Only then you can say what? All the forces on the object are what? Are zero. Okay, which obviously becomes what? A completely what? I don't want to say completely non-interesting situation. It would be, especially if you push something and you let it go forever. But at least it becomes what? A complete neutral space. Okay? So the first statement says that all the external forces on the object have been combined and have resulted in a zero overall effect. They did not cancel each other, they canceled each other's effect. When things cancel each other, they actually completely cancel each other. No, they canceled their effects. This, in other words, the overall collective effect of all of these external forces is nothing. Nothing means nothing is moved. Sorry, nothing means no motion. Okay. The second statement is a complete different in nature. The second statement is even more fundamental. It says that there are no external forces acting on the object. And the only way that is ever going to happen is if the object, if there's no combining forces to be done, which means you are in theoretically deep space. There's absolutely nothing affecting you. And technically, you have to be really far from like galaxies and stuff because again, gravity is it's a good thing that gravitation is a very what, strong but weak force. Gravitation is very weak force. So it does off very, very, very quickly, but you still have to be far, especially if the mass you're near is very, very huge, like a galaxy or a black hole or a planet, and so on and so forth. Okay? All right. All right. Let's do now some examples to really get the idea going as far as what diagrams like we sketched yesterday are concerned. All right. So calculate the net force when each set or group of vectors or forces, I guess, acts on the same object. Sketch an FBD, sketch an FBD for each object. Are you told what the objects are? No, you don't know if they're what, textbooks or cars or pens. So what do you just sketch? Remember the university way? No, the university way. You sketch a thick dot and that's it. You're not allowed to show any size of the object. Okay. So how many forces are acting, or what forces are acting on part A? We have a what? So we have, oh, sorry, that's the answer. My bad. That's the answer. So what do we have here? So for part A, hold on. For part A, I think we have enough space here. All right, for part A. So, by the way, is this one dimensional or two dimensional? Why one? Because what directions do you only have? West and east. Okay, so here is, oops, here's this. Okay, what do we have? We have this much on the west, 5.5 newtons. We have also what? This much, which is how much? 3.4 newtons. And then we have 4.2 newtons. Okay, now how do you write the Fnet statement, everyone? Okay, let me show you a couple of ways. Okay, don't copy this, everyone. Let me show you a couple of ways. Okay, everyone. Forces by nature are what? Vectors or scalars? By nature, they are vectors. So everyone, one way to write this is, look, F net equals, hold on, what was the definition of net again? What's another word for net? Overall. When you do an overall bunch of things, you effectively what? Subtract or add them up. So that means if you're dealing with the force notation, you should write it this way. Look, you should write it this way. F1 plus what? F2 plus what? F3. Okay, that's one way. What if you wanted to do it as scalars? Then you have to what? Make some of them positives and make some of them what? Negatives. So, but let's see how that translates anyway. So how about if I want to do it this way? So let's go back to here. Okay, so F net equals 5.5. Okay, we have to choose a direction to actually flip. Which one should we flip? Those two wests or this one east? Why? Seems that the two west will what? Combine to a bigger effect than the what? Than the east. So 5 plus 5 west plus how much? 3.4 west. Technically plus what? 4.2 east. But from all the weeks we did with one-dimensional vectors, we can what? We can, yes. Which plus negative. 5.5 plus 3.4, 8.9. Take away 4.2, how much? In which direction? In Newton. Thank you. Very good. That's it. Remember, number, unit, direction. Number, unit, direction. Okay. How about the next one? We've got 92 acting which way? Physically up, not north, physically pulling up. And we've got 35 down and 24 down. Okay. So that would be physically up, physically down, physically down. So that would mean 92 newtons this way. How much? 35 newtons this way and 24 newtons this way. So here I will say F net equals what? Okay. If I want to do it with what? If I want to do it with the signs, I have to choose what? One direction to be what? And one direction to be positive. So obviously we can tell that the 92 is going to beat the what? The combined effect of 35 and 20. So positive 92, subtract 35, subtract 24. How much is that? Well, 35 and 24. Well, yes, 33. Okay, technically, what am I using here, everyone? I'm using a vector. So even though you skip the what? The vectors in the middle, what do you have to bring back at the end? You have to bring a direction at the end. Again, if I just ask what's the magnitude of the net force, you don't have to care about that. But I didn't, or the question didn't. You know what? We have to bring back the vector. 33 newtons. Which way is going to win? Up or down? Up, absolutely. Yes, because see, again, we designate up to be positive. So if I got a positive answer, it must be going up. If I got a negative answer, it must be going down. Just like we did with kinematics, same way. Okay, last one. Okay, what do we have here? Is this a 1D or a 2D? Why? Because you've got up and down, and you've got technically right and left. Okay, yes. Okay, look at the numbers. Up is how much? Down, east, west. So really, what ends up happening to this object? Staying still, no motion whatsoever. But let's just sketch the diagram. How much is it? 15 this way, 15 this way, 12 this way, 12 this way. Okay? Okay, here's a question for you though. Oh, what did I say? My bad. Thank you. 35. So is that correct? Yeah. Now, okay, thank you. Yeah, I know I said 12, 12. Question for you. Is this 1D or 2D? Can you add direction in 2 dimensions? You can't. So what do? We have to split into how many dimensions? We have to do the vertical on its own, and then we have to do the what? The what? Horizontal on its own. Okay, so we have to do what? You have to do F net. Everyone look. Let me just zoom in. Again, dimensions never mix. So F net. Okay, what do you call this? What's another name for it in math? Thank you. So from now on, no need to call it horizontal or H. You just call it F net on the what? On the x-axis. Okay. What's the deal here? Is it gonna balance on the x-axis? No, it's not. So we know it's definitely gonna be what? Positive 35. Subtract what? Okay, how much is that? 23 newtons in the east direction. How about F net on the y? We know it's gonna be what? 15 up minus what? 15 down. So 15 minus 15, which is how much? 0 newtons. Again, I know it's 0, but technically it's a vector. What do you have to pin next to it? You have to give me a direction. Now with 0, doesn't matter which direction you pin. Nope, because again, 0, you can think of it as having no directions, or exactly, or any direction you want. Well, you know what? Let's go with up. Everyone, I'm going to go up this way. Physically up. Not north, physically up. Oh my God, I didn't know we had a whole blank slide for this. My bad. So I'll use it when I publish my solution. All right? Okay. I'll give you 1 minute to read the next question and just imagine the situation. What's going on here? A force of 1200 newtons up on a beam. Who knows what a beam is? Uh, so basically what? A steel structure, like a what? Basically a rod that actually what is used, for example, in construction, which experiences a force of gravity. What's another name for force of gravity? One word name. Nope. No. Okay. Everyone, pencils down. Pencils down. No, no. It's no, no. There's a huge confusion sometimes, especially with true false questions. Force of gravity and gravity are the same. Okay. Force of gravity is what? How much force you being what? Pulled down. Gravity could also mean what? Gravity's acceleration. You see what I mean? Are they the same? Are they related though? Yeah, if the moon has what? Less gravity acceleration, it pulls you what with what? With more or less force? The moon. If the earth has a higher gravity acceleration, it pulls you down with what? Why? Because what's the equation for Fg? The small easy one that rhymes. Fg equals mg. M times g. What does that mean? If you have the same mass, but you go to the moon. By the way, did anyone work out the g of the moon? I did publish the results yesterday. Did anyone work out the gravity of the moon? It was supposed to be homework. No. 20 meters per second squared on the moon? Come on, we barely have 9.8 here. No, no, maybe you don't remember, but did you work out the number? Did you? Any? Yeah, how much? 1 point? Everyone, here it is. It was case number 3. Not mad. Just just the fact that what you did not compare it to the Earth. Everyone, there we go. Everyone, that's it. The gravity of the moon, if you calculate it using the what, the mass of the moon and the what of the moon. Come on, mass and this or radius in this case, it boils down to be how much? 1.63. If we divide the one for the Earth, which is how much? By one, you get how many? The gravitational acceleration of the Earth near the surface, though, is how many times stronger than the same one near the surface of the moon? How many times? What does that mean? If you drop this on the moon, does it take this much time to go through, or much less? Sorry, or much slower time? Much slower speed, which means much longer time. Is it making sense? So that means what? What's the G of the moon? How much? Okay, so let's say, for example, we take Yasmin here, and let's say, for example, Yasmin's mass, let's say, is 45 kilograms. On the Earth, she weighs how much? 45 times what? 9.8, which is roughly 440 newtons. On the what? On the moon, how much do you weigh? 45 times what? Which is going to be how many times less? Yeah, if you take a number 6 times less, whatever number you multiply with it is 6 times less. So if you technically step on a scale on the moon, your mass will actually read 1/6 of that, because the needle is now what? Being pressed 1/6 as much. Do you see what I mean? You stand right here on the Earth, you're pulled down at 9.8 meters per second squared. If you step on the moon, you're still being pulled down, but at what rate? 1.6. So that means what? The pressure on, not the pressure, the stress, or the weight on the spring of the scale is 1/6 as much, which means the needle is not going to move all the way to the real weight, sorry, to the real mass. It's going to weigh to 1/6 to the mass. You weigh 1/6 of your weight on the moon. But did your mass change? That's why mass and weight are not the same. Yes. What? Oh, the 20. Oh, the big number that we got, the 20 billion billion. Oh, okay, okay, I see. All right. Say again? Question. Listen up. Yasmin is asking, can the gravitational acceleration go higher than 9? Absolutely. Actually, no. The sun. The sun actually has so much of a gravitational pull. I'm gonna show you, and then you know what? Might as well actually show it to you right now. Hold on, hold on. This one. Mars. Took a while. Moon. Okay. You guys see the sun. The sun is very interesting. I know if you remember it from this one. Pluto is not a planet anymore. It's less heavy, but also what? Much smaller in size. Because remember, it's between, okay, Uranus, white, like almost like that. Saturn. Okay. Jupiter. Okay. Sun. It collapsed under its own weight. And you didn't even see it come because it just got accelerated so hard. Do you see what I mean? Even the weight of the car got pulled down and crushed the tires. That's the sun. Okay. So could it be higher than 9.8? How about this one? Yes, you do. You do. There's no shielding of radiation from in space. Yeah. Well, that's why when they build the space shuttles, they actually have to make sure that it's built with an actual paint that will actually absorb the radiation shield, cosmic shield, background radiation shield, and so on. Okay. What do we have here? What object do we sketch? Yeah. And obviously, we should not sketch a beam. We should sketch just a what? Nah, I'm gonna sketch a beam. Okay. And How do you sketch a beam? Nothing. A 3D long box. That's it. Yeah, what's up? No, but it is identified. Oh, if it's identified, what are you going to sketch? You can sketch a box or a dot. But in university, everything has to be a dot, including, that's the point. Even when they identify it, everything has been compressed to the center of mass of the what? Of the object itself. Okay? All right. So everyone, here it is. Okay, the beam. What is pulling up the beam? All right. A chain could look like a rope for all I care. Here it is. Done. Full mark. That's it. Obviously, you didn't have to go crazy like this. You can just sketch that. Here's a box, and here's a what? Here's the rope. I just like to look fancy every once in a while. What forces? Okay, come on. What forces are on the beam? No, first one always gravity. So I'm gonna point this way and just say Fg. Okay, what's the other force? Okay, my question to you is the tension really like in the beam or in the rope? In the chain. But it's acting indirectly on the what? On the beam. Do you see it? So the beam is under tension indirectly by the rope. That's why I never like to put, I just don't like to put it like this. I don't think this is correct. Do you see what I mean? Effectively, that's what's going to happen. But I never like this way of showing it. I like to actually show it where? Exactly. Inside of the rope itself or near the rope. Now, I think it stands more to what to reasonably what really happened. Okay. Any other forces acting on the beam? Any applied? Well, technically, the only applied one is the one in the what? Is the one in the what? In the rope, yes, and the chain. Any friction? I don't know. They did not even tell us to what to ignore it, but we don't even have any information to what to include friction. And what's the last one? Is there any normal force here? No, no. But is there any normal force here? What if the beam, everyone, was lifted like this? Then there will be what? Normal, because the beam is resting on a what? On a two-dimensional surface. You see what I mean? You need a surface for normal. Even your hand, as long as it's flat, somewhat flat. Okay? All right. So what's the last thing I add to any diagram? One more thing. Motion direction, and there's, okay. I didn't know what's the motion direction. The question didn't say. But we can tell what? Who's winning? Up, which means the motion has got to be up if it existed. Go ahead. Motion. Okay? The question is just saying what? Calculate the net force on the beam. Well, we are ready now to just write the final statement. So the final statement is, my bad, final statement is what? F net equals 1200 newtons up. All right. No, not minus. If I'm using vectors, I'm going to say what? Plus 1100 newtons down. And now one of them is going to flip. That's what you meant. So 1200 subtract 1100, which is how much? Sorry, 1100. Which is how much? 100 newtons in which winning direction? If you want to maintain that you're talking about the vector. Okay. All right. Good. Okay. Last one. Okay. Ali, read the last one for us. Sorry, what's that? Go ahead. Yeah, you push. Uh-huh. Does that make sense, by the way? East and west, because friction never goes what? No, no, it never goes with motion, goes against whatever motion exists. Uh-huh. Yeah. All right. How many forces are mentioned? Is this a smooth surface or should we sketch some roughness to it? There's friction. Okay, what's force number one? Always on Earth, gravity. By the way, could you technically, by the way, do you have all the numbers for all the four forces? I think so. Could you skip FGs for the actual magnitudes? You could, like, instead of saying FG, you could say uh, 7.5 newtons. You could, but please get used to always what symbols on diagrams and numbers where in the equation. Okay, so FG. Okay, what goes against? Let's say this way is east. How much is pushing it? 6.5. Oh, what's the symbol for 6.5? No, no, symbol, symbol. What kind? What is applied? FAPP. And what's going against? No. Well, if there was a rope, I agree with you. Friction. Do you remember where I usually could sketch friction? Yeah, I wouldn't sketch it coming out of the center, although mathematically it does. Physically, it's right here. I know. I like a physical picture. There we go. Okay, which way do you think definitely it's moving? Could it ever move with friction? No, friction never moves you its way. Friction, the worst friction could do is still keep you moving where? Forward, but what? Slow you down. So if you're moving, you are moving this way for sure. Oh, no, no. But that's my point. The worst could happen is slow you down and bring you what? But could it ever just suddenly come to a stop like a spring and then yank its way your way? No way. It's a passive force, never an active force. Okay. How many dimensions are here? One or two? Can we mix dimensions? No, you can't. All right. By the way, is there a proof that these two forces are the same? What? If FG was bigger, what definitely must happen to this object? It has to rupture through the surface. What if Fn is bigger? I guess somehow maybe someone gave it a push and what? Like it flies. But if it's staying still at the same altitude, what does that mean? Same height, same one here, same one here. All right. So let's do everyone. Let's go here. F net. Doesn't matter which one you do first, the y or the x. No, you have to do both. So you choose to do. Let's. You know what? Let's do the canceling one first. Which one canceled? The y or the x? Y, because apparently it did not move at all on the y. Equals fg. Sorry, fn. Or who cares? Plus fg. All right. What's the normal force? How much? 7.5 newtons in the up direction plus 7.5 newtons in the down direction. So really, what ends up happening? Just a big fat zero. Newtons. You know what? Absolutely. You know what? We used up before. Let's just, say we're changing things. All right. Let's do the F net on the X. F applied plus F friction. Applied was 6.5 newtons in the east, plus I believe it was 4.5 newtons on the west. Cancel. I mean, sorry, not cancel. Flip. I mean, which means it will be, yeah,